So far, we have focused on programs written in C and C++. We've examined how vulnerabilities in programs written in these languages can lead to attacks that violate memory safety, resulting in remote code injection or theft of sensitive data. We've also looked at various defenses against these attacks. One effective defense is to use a memory-safe programming language. In this unit, we turn our attention to Internet security, focusing on applications that are part of the World Wide Web. While many web applications are implemented in type-safe languages and thus avoid memory safety issues, they have their own sets of problems. These problems go by names like SQL injection, cross-site scripting, cross-site request forgery, and session hijacking. Interestingly, the issues underlying web vulnerabilities are sometimes very similar to memory vulnerabilities. For example, SQL injection, SQL injection, and cross-site scripting arise because, like buffer overflows, the application's failure to properly validate its input results in it treating data as if it were code. The modern web, sometimes called Web 2.0, brings in the additional complication of mobile code. In particular, when you visit a website, code from that site will be silently downloaded to your machine and then run. Well, how do you ensure that this code does not violate the security of other programs running in your browser or on your machine? The outline for this unit is as follows. First, we will look into the technical details of the basic World Wide Web. We will see how typical web applications are structured at the client and at the server. We'll examine HTTP, the Hypertext Transfer Protocol, which client and servers use to communicate. We'll see how improper interaction with the database on the server can enable an attack called SQL injection. Next, we'll look at how web applications implement ephemeral, that is, short-lived, non-persistent state. Such state is useful during a long-lived session. Typically, ephemeral state is implemented using hidden form fields and cookies. Unfortunately, sloppy use of these features can lead to attacks such as session hijacking and cross-site request forgery, or CSRF. With these attacks, an adversary can take over a user's account or manipulate an application to act for that user, but in the adversary's interests. Finally, we'll look at so-called Web 2.0, which characterizes the modern web. The modern web makes heavy use of mobile code, often written in the language JavaScript. JavaScript programs originate at a server but run at the client. Running code at the client creates new possibilities for attack, one of which is called cross-site scripting, or XSS. With XSS, a user is tricked into running code he thinks is from a trusted website, but in fact is from a malicious source. Throughout the unit, we will look at various defenses to these attacks. One common theme of all of the defenses should be familiar: validate your input. So, let's begin by looking at the basics of the Web 1.0. So let's begin by going over the basics of the World Wide Web. The World Wide Web consists, roughly speaking, of two sorts of participants, clients and servers, and clients and servers interact with one another. So clients consist of things like laptops and desktops and mobile phones, all of which are interested in content that's provided by servers, and these are things like shopping websites, Amazon for example, or information websites like Wikipedia, blogs, things like that. So the client runs a browser. This is Internet Explorer or Chrome or Firefox. And at the server, one runs a web server to serve the content. And web servers are things like Apache HTTPD, Nginx, IIS by Microsoft, and so on. The server often maintains a database which keeps track of the information that it's serving, and the client might also maintain a bunch of private data that's relevant to the interaction that it's having with the server over the web. The database is often a separate entity, logically and sometimes even physically. So for example, a database might be MySQL, that's a particular database management system, or Postgres, or SQL Server. Much of the user data is stored as part of the browser or might be stored as files that the browser later has access to. When the browser interacts with a web server, it does it via what's called a Universal Resource Locator, or URL. And we see one here. This is the URL for my homepage at the University of Maryland. So the first part of the URL is the protocol, here HTTP, which we'll talk about in a minute. The second part is the address of the host that is serving the content, where on the internet the server is. And this is translated into an Internet Protocol, or IP, address by the Domain Name Service, or DNS. So when the user types in www.cs.umd.edu, this address is provided to DNS, which will then look it up and return back an IP address, which is just a 32-bit integer. In this case, it's 128.8.127.3. With this information, the browser knows that it should connect to this internet address using the HTTP protocol. The remaining part of the URL is the path to the particular resource that the client is interested in the server providing. Here, it's ~MWH/index.html. If we look just at the last part, the index.html part, we can see that it's a file. It's static content because of the suffix HTML. So basically the server is just going to acquire this file and return it back to the client. Because it's hypertext, HTML, the browser will render that file on the browser screen, and the user can interact with it, clicking on links and filling in forms and so on. Another sort of URL might have a different final file, a different path. So in this case, delete.php, and the content of that path is different. PHP is a program written in the PHP programming language, and the content is actually determined by running the program. PHP runs at the side of the server, and it will query the database to acquire information. So if the database changes because other users interact with it, then the next time you go to delete PHP, you might get different content shown in your browser. So this is a dynamically generated file. It's content that's created on the fly. Now sometimes URLs also have what are called arguments that direct how the server is going to do the rendering for dynamic content, how it's going to produce the page that's ultimately returned back to the client. So here we have a couple of arguments, F, which is set to Joe123, and W, which is set to 16. Okay, so the browser communicates with the web server using the protocol that's specified in the URL, and the most common one, the one we'll focus on, is HTTP, and this stands for Hypertext Transfer Protocol. It's a so-called application layer protocol when using the OSI network stack model, and it runs on top of TCP, the Transmission Control Protocol, which can exchange collections of data reliably across a network, even an unreliable one. So what will happen is that a user might be viewing a web page and click on the web page, and as a result, an HTTP request will then be sent to the server that was specified in the URL associated with that button click. This URL is accompanied by headers in the actual HTTP request, and we'll look at those in a moment. And there are two types of requests, GET and POST requests. GET requests are such that all of the data is in the URL itself, this data being the data that determines what file or content is returned. Importantly, it will not change the contents of data that's stored on the server. It will only cause those contents to produce a file that is sent back to the client. A POST, on the other hand, which can happen by filling in a form field and then submitting it, may allow the server's state to be changed. In other words, it may have side effects. So here's an example of an HTTP GET request, and in this case it is to reddit.com. And we can see at the very top the URL, and most importantly, the first two lines say that it's a GET request, and it's going to the R security path using HTTP version 1.1, and it's going to get it from the host www.reddit.com. Another interesting field another interesting header, I should say, that's shown here is the user agent field, and this typically identifies a browser. So this is what the server can use, for example, to provide content that depends on the browser. Like when you go to download a open source program and it knows that you're running on a Mac, it will know this by looking at the user agent field in the header. Okay, so let's suppose we are at this site and we follow that link, and this content is then shown to us in our browser, and we want to click on this worst DDoS attack of all time link that's shown here. Okay, when we do that, it will generate an HTTP request that goes to zdnet.com and gets the URL that we clicked on. Notice here something different from the last header, the set of headers we looked at. There is a so-called referrer field, and this indicates the web page that was clicked on in order to generate the current HTTP request. And this can be useful for the server to know whether or not the request was generated from content, say, that it produced, rather than from content that someone just typed into the browser. And this does have security ramifications. We'll look at those more a bit later. Now let's look at an HTTP post request. So here we're posting on a site called piazza.com, which is a course management site that allows you to have online discussions and so on. Here we can see the request at the very top has post as the request type, along with the URL again, and we can see the host is piazza.com. Much of the rest of the request looks similar. Here's one part that's different. The very end includes data that is explicitly part of the request's content. So for example, these are this part of the request might be populated by form fields that are filled in by a user, for example, when responding to a blog post. So you can see here at the very right a bit of HTML. Interesting, perhaps it has to do with and so on, that someone might have typed into a text box that then got included in this post request when they clicked submit. On the other hand, you can still also have content included in the URL, just like you might for a GET request. Okay, so once you've submitted a request, now you're going to get back a response that the browser is going to render. And what does the response look like? Well, it will contain a status code, some headers, and then the data. As well, it will contain some cookies. We'll talk a whole lot more about cookies later. But roughly speaking, these represent state that the server would like the browser to store on its behalf that helps maintain the notion of a session or other sorts of memories that the server would like to have in terms of interactions with the client later on. So here's an example response. At the very top, we can see the HTTP version, the status code, and the reason phrase. So here the status was 200, which means that it could find the page that we asked for, hence OK for the reason phrase. Then a whole bunch of headers, and finally the data at the very end. You can see here set cookie as a part of the header. These are those cookies I was speaking about before. And you can see things like at the very end, content type text HTML that indicates the type of the data that's being provided. The browser can then use this content type specifier to know what to do with the data, how to render it on the user's browser window. In a web application, the persistent or long-lived data resides in the database. This is things like personnel records or credit card numbers, online inventories. And of course, this sort of data needs to be protected from illicit access and tampering. Even web applications that recognize this and do try to protect it sometimes fail because of a bug that allows a very clever sort of attack called an SQL or SQL injection. So in this unit, we're going to look at that attack, but to do so, we're first going to have to talk about how data tends to be managed and how it's accessed using a special language called SQL. So typically for an online server application, we want to support ACID transactions on our persistent long-lived data. What's a transaction? Well, it might be a transfer from one bank account to another, or a purchase of an item from an online store. ACID stands for, first, atomicity, and this is to say that transactions should complete entirely or not at all. That is, you should either completely purchase the book or not purchase the book, but you shouldn't pay the money and then not receive the book. Or you should transfer $100 from bank account A to bank account B. You should not withdraw the $100 from bank account A, but then not deposit the result in bank account B. Consistency means that the database is always in a valid state. That is, as far as other concurrent queriers of the database are concerned, all of the data in the database is in the state that you expect. Intermediate states of transactions, like I've withdrawn the money from one account but not yet put it in the next account, should not be visible. Isolation basically says the results of a transaction aren't visible until an atomic operation completes. And finally, durability. Once a transaction is committed, it should be persistent, durable. Even if there's a power failure or some other sort of failure, the effects of that transaction should persist. Now, achieving ACID transactions is no easy feat. Fortunately, the research community and industry have done a great job over the last 3 or 4 decades putting together systems called database management systems, or DBMSs, for managing data and supporting transactions on that data that provide the ACID properties. So the standard way, maybe not entirely completely the standard, but a common way anyway, of storing data is in tables and accessing those tables using the standard query language, or SQL. So here on this slide, we have an example of a table. The name of the table is users, and the table consists of a bunch of records where each field of the record is referred to as a column. So here we see that we have 5 tuples, a record with 5 elements, name, gender, age, email, and password, and we have 4 records stored in the users table. Now, we can use SQL to read from this database and to write to it, update it in various ways using different SQL commands. So the most common SQL command is probably the select command, and it gives you a way of querying the contents of a database. So this particular select command says, look at the age fields in the users table and select all of them where the same record as the age has the name D. So looking at the table, we can look at the age column and find, we can look at the name column to find the users whose names are D, and then select out the age column from those records. So in this case, the answer would be 28. Another SQL command is update, and this gives us a way to modify records that are already in the database. So this update command says we want to set the email address of all users whose age is 32 to be the email readgood@pp.com. So if we look at the users table and we look at all of those users whose age is 32, there is only one. It is the third record, Charlie, and so we should update the email address of that record to be readgood@pp.com. Another command is the insert command. This gives you a way to add new records to the data, to the table, and here we're inserting into the table a record Frank, who's male, and 57, and so on. Finally, there's the drop command, which gives you a way of removing data from the database. Here we show how drop can be used to delete an entire table from the database. Now, server-side code will interact with the database using SQL, and one common way that server-side code is written is using a language called PHP. So PHP is looks like a hybrid of HTML, which is the standard markup language for rendering web pages, along with some extra code that allows the program, the PHP program, to query the database and substitute the results of that query into variables in the PHP program that are eventually rendered. So this is a very convenient and popular way of writing dynamic content generation from asking a database questions and then putting the results in the generated web page. So here on the slide, we see a website where we see a couple of fields, username, password, and a button. And we can suppose that when the user clicks on the login button, he will have filled in the username and password fields, and these will have been included in arguments to the URL that was sent along with the HTTP post request. So let's suppose then that a user types in their username and password and sends that information along. That information is going to be included in the user and pass variables shown in the PHP code. So what is that doing? Well, I've logged in as user, and the query is going to select star from users, so it's going to get every possible user in the users table where the user's name is the user that was typed in and the password is the given password. So let's suppose that you can fill in that user field however you like. The question is, could you exploit this situation by being clever in your choice of what the user field contains? And in this particular case, the code is vulnerable to a SQL injection. How? Well, suppose we fill in the user field with this data: Frank, close quote, or 1 equals 1, close paren, semicolon, dash dash. So this text is going to be substituted in for the $user field inside of the query that's being constructed as a string in the MySQL query call to the database. And after substitution, this is what the string will look like. I'll take the Frank close quote and stick it in for user along with everything else, or 1 equals 1, semicolon, dash dash. But what you can see here is that the way that the string is constructed, what we've done is we've effectively modified the query that's going to be sent to the database. The Frank close quote closes off the user as if the user was Frank, and the or 1 equals 1 is another element of the where clause for the query. Dash dash is a comment, so that's effectively causing the SQL interpreter on the database to ignore the and password equals portion of the query. What's this query going to do in the end? Well, it's going to select every user whose name is Frank or 1 equals 1. Well, 1 always equals 1, and so this query will always succeed, and effectively this will return the entire contents of the user's table. You can even chain together statements with a semicolon. Here, by adding the semicolon drop table users dash dash, once we substitute in, we'll do the select to grab all the records from the database and print them out, and then we will delete the table by writing drop table users. So this is very bad. A very obvious way of coding things, just putting in the user and the password, has opened us up to the possibility that malicious input can effectively change the form of the query and cause private information to be returned or sensitive and important information to be deleted. And SQL injection attacks are quite common. They're less common than they were a while back, but they're still a significant source of vulnerabilities. So at this point, you should know enough to understand this XKCD comic. The great thing about the comic is that at the very end, it indicates the solution to the problem, a solution we've seen many times before, which is to sanitize your database inputs to prevent these sorts of injection attacks from taking place. And in fact, that's exactly what we'll look at in the next unit. All right. So if we're going to understand how to defend against SQL injection attacks, we have to understand the underlying issue that makes those attacks possible. And that issue is the following. One string combines code and data. So this is similar to what happens with buffer overflows. When a user types in more characters than a buffer can hold, then in an attack like a stack smashing attack, those extra characters will overrun the buffer's contents and corrupt control flow data like the return address or function pointers that then can manipulate what the program does. In the same way, we can think that the code and data boundary is blurred in an SQL injection, and in a sense we're overflowing the contents of that user field and inserting new code to change the structure of the query. So in general, when the boundary between code and data blurs, we're going to open ourselves up to vulnerabilities. So we can see the underlying issue by viewing the SQL query that we intend as a parse tree. So if you look at that query, you can see that a select statement basically has three parts. First, it's what to select. In this case, it's star, that is all possible records. Second, it's which table, in this case, the user's table. And then third, the where clause that refines which records should be considered. So we represent that here as a tree, where the first node of the tree is indicating the select command, and then the three children from that node are the three elements of that sort of command: star, which record, how many records or which records, users, which table, and finally the where clause. Now the where clause itself can be deconstructed into a tree. It's basically the conjunction of two equalities. It's saying that the name field of the records selected from users should be equal to the $user contents, and likewise the password field, that is the password column, it should be equal to $pass. So this should be data and not code. That's our intention. Whatever we stick here, it's going to be a string that's checked for equality to name. Unfortunately, by the way we're constructing this query, we actually will create a different parse tree by putting in a clever input like frank, close quote, or 1 = 1. And that's what we want to stop. Okay, so we hinted a moment ago at the end of the last unit that we should stop it by using input validation. We should check user input to make sure that it adheres to the form that we expect, and therefore only use data that's trustworthy. And we can make data trustworthy. We can validate it in two ways. We can check that it has the expected form, or simply we can sanitize it by modifying it or using it in such a way that the result is correctly formed by construction. So one kind of sanitization is blacklisting, and one kind of blacklisting is to delete the characters you don't want. So a blacklist is a bunch of bad things. So what we could do is we could look in the input for these bad things and we could delete them. So what are some bad things we could delete? Well, we could delete the quote or the semicolon or the dash dash because those were important elements of that SQL injection attack. Unfortunately, this is not going to work in some cases. That is when those characters have meaning in reasonable contexts like the name Peter O'Connor. Another kind of sanitization is called escaping, and instead of deleting characters, escaping would have you change problematic characters to be safe ones instead. So here we could we could escape out the quote, semicolon, dash, and so on with the escaped versions that won't be interpreted in a controlled flow changing way in the constructed query. So you can do this using libraries and so on that are provided in various frameworks you might program in, like in PHP. Now the downside here is that even still you may want to have some of these characters in your SQL, and so this approach is not going to work. Now on the checking side, you could use a whitelist to check that the input is reasonable and simply reject it if it's not. So for example, we saw this in C programming that you can make sure that an integer is within the correct range. That is, say the length that's specified by a user is no greater than the actual length of the buffer, the length it is referring to, and then reject the input. And the idea here is that it's safer to reject an input than it is to fix it. And the reason there is that a fix may actually produce the wrong output. That is, an attacker can manipulate the attempt to sanitize something to actually corrupt it to his needs. So this is following the principle of fail-safe defaults. That is, do the simplest thing and reject the rest. And we'll look at that principle actually in more depth later on. It turns out that whitelisting can sometimes be hard because it's hard to specify what the whitelist should be. For example, if you only want to allow reasonable first names, well, how do you know what the reasonable first names are? Will you provide a specific dictionary that needs to be iterated through to check the names against? It could be both expensive and difficult to get right. So for SQL injection, SQL injection in particular, the preferred solution is to use what are called prepared statements. And the idea here is to treat user data according to a type, therefore decoupling strings, the use of strings as code from the use of strings as data. So here's our query again. Here's the same query expressed as a prepared statement. So the first line creates a handle to the database, and the second line creates a prepared statement template. You can see that this very much resembles the string that we were constructing before, but the prepared statement instead includes everything other than the parts that are to be filled in, and those it designates with question marks. The filling in comes as a separate statement happening with the bind param call, and here the bind param call takes a format string which specifies how many arguments are to follow and what the types are. So the statement has two question marks, so it expects two arguments, and therefore the format string has two format specifiers, here SS, where S stands for string. So when user and pass are substituted in to the statement that's created by the prepared statement, it will treat those data as strings and not misinterpret them as code. And then the query can be sent to the database. So we bind the variables, we type them, and as such we have decoupled compilation specifying the template with the binding process of the data. So using a prepared statement, we would replace the original query shown above with this query. And as such, the binding is only applied to the leaves where the purple parts are specified, leaving the structure of the tree fixed. So if we had filled in the username with Frank or 1 = 1, as we did in the beginning, it would be fine because it would not change the structure of the query. It would simply be an odd username to be looking up in the database. Now, prepared statements make it possible to eliminate many SQL injection attacks, but sometimes queries are complicated and mistakes can be made, so you have reason to want to use defense in depth to mitigate the impact of a SQL injection should it happen. One way to do that is to limit privileges, that is to reduce the power of the exploitation by not allowing the server application to do anything it wants when accessing the database. So for example, when you connect to the database, you can indicate to the database that only certain commands should be allowed. For example, only select queries on the orders table, but not on the credit card table. You can also choose to encrypt sensitive data stored in the database. So if somehow the database is stolen, that data is going to be less useful. You may not need to encrypt some of the tables, like the orders table. So when encrypted data is selected from the database, it is then decrypted inside of the server application using a key or a smart card or some other sort of mechanism. But while it's stored in the database at rest, it's encrypted. What we have seen so far has been pretty simple in terms of interactions. The client sends a message and the server responds. But how about multi-message interactions that might be part of a longer session? In particular, in perhaps your own experience, you are used to a session lifetime in which the client connects, the client sends a request, the server responds, the client issues another request whose content is based on the server's prior response, the server responds again, and so on until finally the client disconnects. Given this experience, you may be interested to know that HTTP has no notion of state or memory. Each request-response pair is completely independent at the protocol level. At the least, this should make you wonder, well, how is it I don't have to provide login credentials with each request so that the server knows it's me each time? The answer is that web applications themselves keep track of the relationship between requests and responses in a session. They do this by maintaining bits of state that relate the requests one to the next. Next, we'll look at how this is done. So in addition to the long-lived state that is going to be stored in the database at the server, so this will have things like credit card numbers and user account information and inventory and things like that, the web application will maintain ephemeral state that aids the server processing while a client is interacting with it. So this is not long-lived state that must be durable, but instead it's keeping track of what a client is doing during an interaction to relate one request to the next. So in order to maintain this state on the client rather than the server will actually send an encoding of it back with each response, and then the client can return that state to the server when it makes its subsequent requests. And there are two ways that we can implement things this way. One is to use hidden fields in the HTML documents that are communicated back and forth that the server generates, and the other is to use something called cookies. So let's look at hidden form fields using an example for an online store. So here on the left we see a web page from socks.com. It's the order.php page. And let's suppose the client has navigated, the user has decided to buy this pair of socks for $5.50 and clicks the order button. Now the server will receive that request and send a page in response. And notice that this page says that the order is $5.50. So the user is going to confirm that order. Now the question is, how will the server relate the $5.50 request that the server chose on the first page so that when he or she clicks the yes button on the second page, the server makes the right order? Because HTTP is stateless. It's not remembering, technically speaking, one interaction to the next. And the answer is that the server can embed this information, the cost, for example, of the socks, in the web page that it responds with, that is the pay.php page. So here it is presented to the user, and notice here we have what's called a hidden form field. So a form is just an HTML element that has a button associated with it that will produce a web request. And there are two non-hidden form values, yes and no. They're shown at the bottom of this HTML code, value yes, value no. And then there's this hidden one, the value $5.50. So this hidden value will get sent with the request when the user presses the button. Now here's the code, the PHP code on the back end at the web server that will receive this web request, and it will pull out the form field values, pay, that this was a pay request, and price, and as long as the price was not null, it will debit the credit card that amount and deliver the socks. Here's the problem though. Price comes from the user. It's filled in by this form field value. Well, because the HTML is sent to the user, a clever and malicious user can change the value to be something far less than the vendor intended, and therefore corrupt the computation. So we can get around that problem by using hidden form fields of a special variety that we call capabilities. So the server will maintain trusted state. Instead of sending the state to the client, the server will keep track of the state, but it will index that state by a capability that gives the client access to it. And what is a capability? Well, a capability is a right. It's a piece of data that gives a client who possesses it a right to perform some action. And that capability should be unforgeable. By definition, that would prevent us from waging the attack that we saw before, which was that the client was able to change the price. Because the capability is intended to be and should be unforgeable, the client will not be able to change it to effectively change the price. So given that capability, the client will reference it in subsequent responses and therefore be able to access the state. To make capabilities unforgeable, a typical approach is to make them large random numbers, so they are difficult to guess, and therefore if a client does attempt to make a guess, the client is very unlikely to find a number that corresponds to a real capability and therefore has no power. So here's what the page looked like before. Here's how we might change it to use capabilities instead. So now the name is SID for capability, and the value is a random number. On the server side, we will modify the code to look up the SID to find the price, and only if the SID is legal will the price be present, in which case we'll bill the credit card. If it's not there, then we'll go to the else case and cancel the transaction. So, capabilities of this sort can take us quite a long way, but they aren't perfect. We don't like to have to pass around hidden fields all the time. It complicates the interaction amongst all the pages. It's sort of difficult to put together a web application that way. And it has the big drawback that if you ever close the browser window, you throw away the HTML that contained the hidden form fields. And therefore, if you reopen your browser and reconnect to the site, all memory of your prior interaction is gone. So we can solve these problems by using what are called cookies. Just like with capabilities, the server will maintain some trusted state, and that state will be indexed by a cookie rather than a capability. Just as with hidden form fields, the server will send along cookies along with any responses, and the client will then store them locally. When the client reconnects to the server, they will send the cookies in response. Now, instead of these cookies being embedded in an HTML page, they're actually stored, they're sent around as part of the HTTP protocol, and so they're just stored on the disk in an area that's associated with the browser. And so it doesn't matter if you close the page, and it doesn't matter exactly what's on the page during the interaction. So here's an example HTTP response that contains cookies. One of the headers, well, many of the headers, as we can see here, have the form set cookie, and what follows is key equals value, which indicates that the cookie key is the key, and it's associated with that given value. And then there are a bunch of options that specify things like timeouts and paths and hosts and so on. So let's dig into that and look at this example in further detail. So here on the client, it receives that HTTP response and it sees this set cookie header, and now it's going to process it. The first thing it does is it says, well, the key is addition and the value is US. And the options for that cookie are that the value expires as of the given date, perhaps when the session expires, and the cookie is associated with the domain zdnet.com, and URLs at that domain that begin with the subdirectory /. So in short, whenever a client interacts with the server via his browser, if the interaction is with the given domain with the prefix of the given path, then this cookie should be sent along with that HTTP request. So in particular, here is that HTTP response that was received by the client. We see a bunch of cookies are being set here. In a subsequent visit, notice we're visiting zdnet.com and the root directory. And at the very bottom there, we see the header that says, well, we're going to provide the session zdnet production cookie, and we include its value. And you can see that this matches the value that's given on the last line of the response at the top, followed by another cookie, which is ZD region, followed by further data that's again shown at the top, and so on. So all the cookies that are relevant are going to be provided along with the request. There are several reasons that web applications use cookies. The most common use, as we've hinted at already, is for a cookie to act as a session identifier. Basically, after the user logs in as part of a POST request, the application sends a cookie in response that identifies the user. The cookie is sent in subsequent requests to the same web application, so that it can silently authenticate the user each time. The human user, of course, is unaware that this is happening and interacts naturally with the system. Another use of cookies is personalization. Shopping websites, for example, are interested in showing you things that you are interested in. They can figure out your interests based on past interactions. Based on observations, a site can create a cookie that identifies various interests. This cookie can be used to prioritize the display of various elements of the site, effectively personalizing the site to you. Personalization can even go to the level of font choices and other superficial elements of the display. The nice thing about cookies is that these can be anonymous. Such preferences are not security sensitive, at least from the site's point of view, and so no authentication of the particular user is needed. Of course, the flip side to personalization is tracking. Instead of personalization cookies being used only by a particular site, they can be made available to other interested parties like advertising networks. How can this work, given that cookies should only be visible to the site that created them? One way is the following. Site A uses advertising network B to show an ad. When B receives the request from your browser to show the ad, it can figure out that the ad was displayed when visiting Site A. How? Well, by looking at the refer attribute of the HTTP request. For example, the request to show an image. Site B would like to associate you with a list of sites and the pages on them that you tend to visit. In this case, it would like to include Site A. One way it could do this is to maintain a list in a database mapping IP addresses to site lists. The idea would be you are associated with a particular IP address, and the list is then associated with that address, and therefore you. But doing this isn't so reliable because you are not associated solely with one IP address. And in fact, different people might use the same address. Instead, what will happen is the ad network will store the site list as a cookie on your machine. This cookie is called a third-party cookie because it is associated with Site B, but was created when visiting Site A. This way, when you visit other sites that happen to use the same ad network, the ad network's cookie will be accessible to the ad. It can then add to the cookie the current site. It can even customize the ad that's shown based on previously visited sites, which reveal your interests. Now, one way to prevent this sort of thing is to disable third-party cookies. But this method is not perfect thanks to the ability to otherwise fingerprint your browser. But that's a topic for another time. Let's get back to considering session cookies and how we can protect them. As we've already mentioned, an extremely common use of cookies is as session identifiers, which associate a user with a multi-interaction session with a website. The basic idea is simple. The user first logs into the website, for example using a username and password. On successful login, the server sends back a session cookie with the response. Subsequent requests to the same site will also send along the session cookie. This cookie will either go in an HTTP header or will be explicitly included in a hidden field. At this point, the server now knows who it's talking to. This approach makes the session cookie a prized commodity for attackers. In effect, a session cookie is a capability to access a site with credentials of a particular user. Thus, this capability needs to be protected from theft. Otherwise, an attacker can impersonate a user and perform actions on her behalf. Such actions could result in lost or corrupted data, like your bank account balance. To see how theft could happen, consider where cookies show up in an interaction. First, they are generated and possibly stored at a server. Then, they are transmitted between the server and client and back again. Finally, they are stored at the client for later use. As such, cookies could be stolen by compromising either the server or client and copying them, or if the server's algorithm for generating cookies is known, an adversary could predict what a particular user's cookie is. Cookies could also be copied by sniffing the network to observe them in transit. Or the network could be manipulated into sending the cookies to an adversary directly, using techniques like DNS cache poisoning. Cookie release due to compromise can be prevented by building more resilient clients, servers, and DNS caches. In other words, avoid buffer overruns and the other sorts of errors we've already seen. Now, cookie release due to sniffing can be avoided by using encrypted connections. In particular, sensitive interactions after a login should use secure HTTP, called HTTPS, which encrypts the communications, including the cookies. In fact, by setting the secure attribute of a cookie, you can ensure it will only be sent over HTTPS and never over simply HTTP. This failsafe prevents a coding mistake from inadvertently revealing a session cookie. To avoid allowing the adversary to guess what a cookie will be, applications should generate cookies that are long, so that there are many possibilities for the adversary to try to guess, and random, so that the particular possibility is hard to predict. Note that the same guidelines should hold for generating SIDs in hidden form fields. Now if, despite these protections, a cookie is stolen, session hijacking can be further defended against by not using only cookies to identify a user session. Instead, you can build your application to require correlating information on the site that identifies a user's current interaction. For example, if the user is currently looking at a web page that shows his bank accounts, but then a request comes in asking for a transfer, the website should be able to tell that the request is not valid. This can be done by storing hidden fields on pages or using the referrer attribute so that impossible requests, even with a proper cookie, are rejected. This same sort of protection is used for CSRF attacks, which we will discuss shortly. There are yet more mitigations against attacks due to stolen cookies. To motivate them, consider a recent Twitter vulnerability. Twitter uses a single cookie called auth token to identify a user. This cookie is computed from the username and password. Now, this approach suffers from two weaknesses. First, the auth token does not change from session to session. Second, it does not become invalid when the user logs out. This means that stealing the cookie gives an attacker indefinite hijacking of a user's account. Now, the defenses we've already discussed can reduce the chances that a cookie is stolen or that it is used inappropriately. But there are two more defenses we can add. First, do not allow session cookies to go on indefinitely. They should have an expiration date. Now, this is like the expiration date on your credit card. It cannot be used after that date. The other defense is to direct a cookie to be deleted from a user's machine and from the server once a session ends. This reduces the time that a cookie is exposed to possible theft due to compromise. Finally, let us consider a non-defense. You might think that you could neuter an attack by tying a session to a particular IP address. That is, a user logs in from one machine, and if requests come from some other machine, they must be bogus and should be rejected. Now, this defense will work most of the time, but there are sufficient problems that it is not usually deployed. In particular, a user's IP address might legitimately change during a session. If using a mobile device, it could legitimately roam, for example, between networks. It could also be forced to renegotiate an address using the DHCP protocol for other reasons. In these cases, a user would suddenly be denied access. In addition to these false positives, relying only on network addresses will miss some attacks too. One example is when a user's machine is behind a network address translator or NAT device. In such cases, hosts beyond the NAT box will view all clients behind the NAT box as having the same address. The NAT box internally translates this address into different local addresses. As such, in a setting like an internet cafe, it's not unlikely that all machines in the cafe will have the same external address. And as such, one machine in the cafe could hijack a session of another machine in the same cafe, for example, by sniffing the network. Once again, the right defense here is to protect the session identifier. Next, we'll look at a related form of attack called cross-site request forgery, or CSRF, that requires similar and complementary defenses. Recall the two main kinds of web request, GET and POST. GET requests are meant to be reads of the server state. As such, they are not intended to affect modifications to that state. Nevertheless, they often do just that. With this in mind, consider the URL to the banking website shown here. Suppose a user is logged into this site with an active session. What if an attacker is able to trick the user into visiting this link? The outcome for the user is not good, an unintended bank transfer out of his account. The question is, what would convince a user to visit this link? So here's how this could happen. Suppose the client is logged in to the banking website and at the same time is surfing the internet and ends up at attacker.com. Attacker.com returns a page back to the user, and that page contains this tag, where the tag includes a reference to the URL that we saw before. Now the browser, upon seeing the image tag, will automatically visit the URL to obtain what it believes will be an image. So it will go to bank.com and send the request. Now normally, if the user was not logged into the banking website, bank.com would reject the request because the user was not authenticated. But if the user happened to be logged in at the same time as when visiting attacker.com, then this request will be accompanied by the session ID that includes the cookie that says that the user was authenticated. And as a result, bank.com will dutifully perform the request. This kind of misdirection attack is called a cross-site request forgery, or CSRF. The target of the attack is a user with an account on a vulnerable server. The goal of the attack is to issue requests on the user's behalf that look to the server to be legitimate. To ensure legitimacy, the requests are issued from the user's browser, which will send along the needed session cookies. For the request to come from the browser, the user must be tricked into clicking a link while logged into a sensitive site. In the previous depiction, this happened when visiting a malicious site which sent a request to a URL embedded in an image tag. The user could also be tricked to click a link in a spam email, which will get sent by the browser. The link could be disguised, for example, by email formatting to look benign. CSRF works because certain sorts of requests to the vulnerable site have the same structure, minus the session information. Let's look into this in more detail. So how can we protect against CSRF attacks? One way to do it is to pay attention to the referrer field that's set by the browser when it sends an HTTP request to the server. Recall the request that we saw in the example earlier in this unit, where we clicked a link on the reddit.com site. Here we can see that the referrer is filled in with the original page on which that link resided. What a server could do is check that when it receives a request, especially one that's sensitive, that the referrer field only includes URLs for that site, or from any trusted location from which the link could have been generated. In our example, the referrer should not include attacker.com and it would reject the request. So only the pages that a user could legitimately reach should be allowed as referrer fields. The problem here is that the referrer field is optional. Not all browsers send it along. One way to deal with this problem is to use what's called lenient referrer checking. That is, we should block requests with a bad referrer, for example, attacker.com in our prior example, but allow requests with no referrer, for example, because the browser just doesn't include it. So then the question is a missing referrer always harmless, assuming that the browser is legitimate? Unfortunately, the answer is no. Attackers can be clever in sending redirect requests and other protocol messages to cause the referrer to be removed. For example, it can bounce a user off an FTP page that the attacker controls, and the FTP request will not include a referrer header. The attacker could also exploit a browser vulnerability and hack the browser to not include the referrer field, or could mangle the web request in transit by snooping on the link. Another approach is to use secretized links. The idea here is similar to hidden form fields, where we used capabilities. Here, the hidden form field will include a secret that the attacker has a difficult time guessing. So recall that the attacker relies on the cookie already being present in the user's cache, so that when the request to the remote site is initiated, the cookie goes along with it. But the attacker does not know what the contents of the cookie are. It doesn't know what is expected on the page that would normally allow such requests. So if in that page we can embed a secret that the attacker wouldn't know, and the server only allows the request if that secret is included, say as a hidden form field, then we protect against the attack that we saw before, that is, attacks initiated indirectly from a remote site. We can even make the secret equal to the value in the session cookie because, as I said before, the attacker has no way to see the cookie. The attacker can only cause the request to go out without knowing exactly what that request contains. And web frameworks help here. For example, Ruby on Rails is a web framework that makes it easy to write multi-tier web applications, and Rails automatically embeds such secrets in the links that it generates for the web pages of the sites it produces. So far, we've seen that the server will produce static or dynamic HTML that it sends to the browser to render. Recall that static HTML is unchanged from request to request, whereas dynamic HTML is generated at the server, for example, by running a PHP program which may query a database. Either way, HTML pages may contain programs written in a language called JavaScript, and these programs will execute at the client and perform further rendering and content production on the page. So here's a little example of an HTML file that may be sent to the client. You can see it has the standard tags. It also has tags script that indicate the beginning and end of a JavaScript program. Here the program sets two local variables, A and B, and then invokes document_write to modify the contents of the page. The contents of the page will include world, the value 3, which is the sum A plus B, and then a closed boldface tag, which closes off the open boldface tag that was at the top. When this program is rendered by the browser, it looks like this on the page. JavaScript is a programming language whose programs, called scripts, implement client-side portions of a web application. These programs run in the browser and therefore make the web experience more interactive. In fact, the web experience is so much better when using JavaScript that people marked the point at which JavaScript came into heavy use as Web 2.0. JavaScript programs are executed in the browser and, as just shown, can be used to alter a web page's contents to determine what is displayed. To access page elements, JavaScript programs use the Document Object Model, or DOM. JavaScript programs can also perform interactive processing. For example, they can track mouse movements to implement drag and drop, or run code to process button clicks. In addition to event handlers being used to update a page, they can be used to issue web requests and to read replies. Requests can be issued asynchronously, leading to a programming pattern called AJAX. This acronym stands for Asynchronous JavaScript plus XML. It first saw use in the early 2000s and then saw widespread deployment in Google Mail and Google Maps in 2004 and 2005. These web applications for email and maps were far more responsive than their Web 1.0 counterparts. Finally, the most relevant part of JavaScript to our discussion now is that programs can read and modify cookies. JavaScript is a powerful programming language with access to sensitive resources maintained by the browser. and therefore the browser needs to enforce a security policy with respect to what JavaScript programs can do. In particular, if I use my browser to visit bank.com to do my banking, but I also use it to visit attacker.com, I don't want attacker.com JavaScript programs to be able to access my bank data. How might they do this? Since JavaScript programs can read cookies, then without security protection, a script from attacker.com could run and alter the layout of bank.com's website, which, say, could be running in another browser window. Or it could intercept keystroke events to sniff the user's password to bank.com. It could read cookies stored by bank.com. If cookies include session identifiers, then the attacker.com script could issue web requests as if they were from the authenticated user. To avoid these problems, browsers implement the so-called Same Origin Policy, or SOP. The browser associates the elements of a web page, including its layout, cookies, events, and so on, with an origin. The origin is primarily defined by the host name that the web page originated from, for example, bank.com. The Same Origin Policy states that a web page's elements can only be accessed by scripts with the same origin as the page. So to be clear, according to the Same Origin Policy, JavaScript programs are limited in the cookies that they access. Here we see a cookie that was set and stored into the cookie cache, and according to the rules, the value should only be reachable by any domain ending in .zdnet.com, that is the origin of the cookie. We can see this in the domain part of the setCookie attribute shown at the top. Any other JavaScript program whose origin is different than zdnet.com will not have access to that cookie. To work around the Same Origin Policy, attackers can try to inject code using an attack called cross-site scripting. Unfortunately, this attack is quite common. For example, here is a CERT advisory about Huawei modems. Notice that it says that the broadband modems include a web interface, and this web interface is vulnerable to a cross-site scripting attack. A cross-site scripting, or XSS attack, aims to subvert the Same Origin Policy. In particular, an attacker can construct a malicious script to try to trick a user's browser into running it as if the script came from a trusted origin. Doing so gives the script access to the sensitive content and pages from that origin. A cross-site scripting attack works by fooling the victim site into sending the script to the user's browser, which will run it with the full privileges of the victim. Let's see how this can be achieved. There are two types of cross-site scripting attack. The first we'll talk about is called stored or persistent cross-site scripting. In this attack, the attacker leaves their script on the vulnerable web server, for example, bank.com. The server will later unwittingly send that script to your browser, and your browser, none the wiser, will execute it within the same origin as the bank.com server. Visualized, it looks like this. First, we have the bad website, bad.com, and we have the vulnerable website, bank.com. Step 1, bad.com injects a malicious script to the bank.com website. Second, a client connects to the bank.com site, and bank.com unwittingly sends the malicious script along with its content back to the client's browser. The client's browser will then execute that malicious script as though the bank website intended to provide it. As a result, that script can do nefarious things like perform attacker actions, such as initiate a bank transfer, or steal secret data like document cookies to send back to the bad.com site. So in summary, the target is a user with a JavaScript-enabled browser who visits a user-influenced content page, that is, a page whose content can be influenced by prior interactions with users, like the bad.com site. The attack goal is to run a script in the user's browser with the same access provided by the server's regular scripts, and in this way subvert the Same Origin Policy. To do this, the attacker needs the ability to leave content on the web server, for example, using an ordinary browser. The attacker might also have a website to collect stolen information. And the key trick here is that the server will fail to ensure that content uploaded to its page does not contain embedded scripts. Let's look at an example of a cross-site scripting attack, the Sammy MySpace worm. So MySpace was a social networking site prior to the rise of Facebook that was very popular, and it allowed people to create custom web pages. Sammy embedded a JavaScript program in his MySpace page. MySpace attempted to filter these scripts, but in this case it failed. As a result, users who visited Sammy's page ran the program, which made them friends with Sammy, displayed, but most of all, Sammy is my hero on their profile, installed the program in their profile so a new user who viewed the profile got infected, and as a result, Sammy went from 73 friends to 1 million friends in 20 hours and took MySpace down for a weekend to boot. The second type of cross-site scripting attack is called reflected cross-site scripting. Here, the attacker gets you to send the bank.com server a URL that includes in it some JavaScript code. The bank.com site will echo some or all of that script back to you in its response, and your browser, none the wiser, will execute the script in the response with the same origin as bank.com. So here this is visualized. The browser will visit bad.com, the nefarious website, and it will send back a malicious page. The client will then click on a link on that malicious page, which will take it to bank.com. The link will contain some JavaScript code. Bank.com will then echo back the link in its response to the user, and the browser will then execute the script as though the server meant to provide it. Once again, the attacker can perform nefarious actions as a result. So the key here is echoed input. Reflected cross-site scripting attacks need to find instances of good web servers that will echo user input back in the HTML response. So, for example, here's an input from bad.com where to the search term it provides the term socks. When this goes to victim.com and it sends the results back, notice that socks are included in the body. Now the problem arises when that input includes scripts. So here's an example script that's included in the URL. If that script is not filtered out, it will be included in the body returned from victim.com, and the JavaScript interpreter running in the user's browser will execute that script rather than simply print it out. And of course, the script will execute within victim.com's origin. To summarize, a reflected XSS attack targets someone who is using a JavaScript-enabled browser to access a vulnerable web service. The service's vulnerability is that it echoes back part of the URLs it receives in its output responses. The attacker goal is to run the attacker's script as if it had the origin of the victim's site. The attacker does this by getting a user to click on a URL that contains JavaScript code. This code is then reflected in the server's response to the browser. And so the browser runs the script as if it were from the origin server. The key here is that the origin server reflects the attacker script unchanged. This indifferent reflection of the input points to the proper defense. Validate the input. In particular, the vulnerable server should either check or sanitize input from untrusted sources. One form of validation is sanitization. In particular, a server can remove all executable portions of untrusted, that is, user-provided, content that it could appear in HTML pages. For example, it might look for script tags and filter them out. Then, instead of running the script, the browser will end up printing it in the document. This might look a little strange, but it will be harmless. Such filtering is often done in the comment sections of blogs. Commenters are permitted to provide rich content like boldface formatting or italics or underlining. and they can express this using various HTML tags. However, they are not permitted to include tags that would demarcate JavaScript code. Blacklisting particular tags like the script tag and removing them from the input is a natural idea. The problem with it is that there are many ways to introduce JavaScript code. You may think you have them all when you actually don't. For example, it turns out that you can embed JavaScript as XML encoded files or as a cascading style sheet, that is, CSS tag. Moreover, even if you found all of the tags that are specifically indicated as allowing scripts, there may be other ways of specifying code that is browser specific. In particular, browsers have often been known to try to be helpful and render mangled input. Such permissiveness is good for making busted websites look okay to a user, but it can be exploited by a clever attacker. For example, such permissiveness was the flaw that allowed Sammy to evade the MySpace filter. Internet Explorer permitted splitting the JavaScript tag into two words, Java and script, across two lines, even though other browsers would not interpret this as being a JavaScript tag. This split tag evaded the MySpace filters. A better validation approach is to use a whitelist. In particular, a site can allow a certain small set of tags. It can then check that the input only has those tags in it. Any other tags that appear, well, in that case, the input is rejected. The same sort of whitelist applies to all elements of a page that could be affected by untrusted sources. Returning to our blog example, a whitelist filter could check that the URLs or other user comments contain only boldface, italics, and underline tags, and no other tags. Or the blog could permit only a more limited language for providing comments. So rather than full HTML, it could allow, say, Markdown. One note: we have just considered two different attacks with strikingly similar names: cross-site scripting and cross-site request forgery. What the attacks have in common is that one site tries to act with the privileges of another site, hence the phrase cross-site. XSS works by exploiting the trust a browser has in data sent to it from a legitimate website. So the attacker tries to manipulate what the site sends to the browser. CSRF exploits the trust a website has in data sent from a semi-trusted browser. So the attacker tries to manipulate what the browser sends to the site. In short, it's all about exploiting trust. The right defense is to reduce that trust as much as possible, in particular by using input validation. This theme comes up again and again in web security, and indeed in distributed system security generally. Let's finish off this unit with one more example. One popular framework for writing web applications is called Ruby on Rails. Server-side web applications are written in the Ruby programming language, and the Rails framework makes it easy for these applications to work by the web. Parameters in web requests sent to Rails applications can be Ruby objects encoded in XML, or as a format called YAML within XML. YAML is particularly desirable because it's easy to read and Ruby has good support for it. In particular, Ruby makes it easy to encode Ruby objects into YAML and likewise decode YAML strings into Ruby objects. When those Ruby objects represent integers or strings or enumerated types, then web app behavior proceeds as we might hope. However, YAML can encode any object, which it does by embedding Ruby code. Since the default YAML decoder can be used to decode arbitrary objects, it can thus decode arbitrary Ruby code. With a little work, the decoder can be made to invoke the code of the objects it has just decoded. This means that an attacker can send a carefully crafted message to any Ruby on Rails application and get it to run code on the attacker's behalf. Whoa. Once again, the problem here is accepting input without validating it. The problem is hidden from the application developers because the bug is in the Ruby on Rails framework and not the application. A fix to validate the input might be to reject YAML altogether, or to reject YAML encoded objects that embed code. Of course, as with XSS, Holes in the filters mean that vulnerabilities will persist. To conclude, web security introduces a plethora of vulnerabilities that application writers must guard against. All of them can be boiled down to mismatches with trust. If we cannot completely trust the source of some input, then we must validate that input to make sure that it cannot cause harm. When considering means of validation, checking is preferred to sanitization, and whitelisting is preferred to blacklisting. In our next unit, we will see how input validation is just one instance of a general set of principles we should follow when designing secure applications. Okay, welcome everyone. I'm pleased to have with me today Kevin Haley, who's Director of Semantic Security Response at Symantec, and we're going to talk about hacks and defending against them and trends and all kinds of fun stuff about cybersecurity. So Kevin, welcome.
Thanks for having me.
So I wonder if you could tell us a bit more about your background and how you got involved in computer security work.
Well, it's interesting, when I was first getting started, there really wasn't strong computer programs in schools, and certainly no computer security programs. So I came up through a computer company working on operating systems. I have a good knowledge of those, and then found the security area interesting and got engaged in that. And it's been really a terrific experience. It's an ever-changing field. No day is like the other. And we spend a lot of time protecting people against the bad guys, so it's pretty satisfying work.
And can you say more about what it's been like to work at Symantec, how long you've been there, and maybe more about your job title and what you do?
Sure. I've been with Symantec for 16 years. I've had a variety of roles, mainly in product management, where I have worked on security products for mail servers, for gateways, and for desktops. So the product that many people are running at home, the Norton product on your desktop, or at work, the Symantec or Symantec Endpoint Protection product, I've had a hand in those. For the last 6 years, I've been in our research area. This is security response, where we are looking at the latest threats. We're trying to figure out how to protect our customers from them. And we actually receive malware from our customers. And so we are responding to about 1 million new threats every single day and pumping out protection for our customers so that we can update those systems and keep them protected from the latest threats.
Oh, fantastic. So maybe we could dig into that a little bit. Symantec, because of its pervasive security products, the ones you were just mentioning, right? It's running on a lot of people's desktops, on their, whether at work or at home, and so obviously those products are on the front lines. They're seeing what's happening, and the information that they observe, I presume that you guys are able to take advantage of that information and figuring out what the trends are, what the adversaries might be doing, and that helps you craft a response. I wonder if you could say more about what you've been able to learn about trends and sort of the state of security today, and how you take advantage of the information that you have.
Yeah, absolutely. That's one of our great sources of information, is the feedback that's coming from all those systems. They let us know about detections that we've made, what we've detected, where we've detected from, so we've been able to gather information there. We, of course, have honeypots out on the network. We have researchers that are out there looking for new things as well. But it's that feedback from customers, the automatic feedback built into the products themselves, and our customers' ability to send us suspicious files that give us a great deal of data and to be able to track and see different trends. Probably the most significant trend that I've seen, having been here for a number of years, is the change from kind of the noisy malware looking to try to make a name for themselves, the people writing it, to the criminalization of it, which we first started seeing around in 2005, 2006, where today the vast majority of malware is written by criminals looking to steal money or information and data that can be turned into money from you. And then, of course, in the last several years, the nation state type of use of malware for cyber espionage, and of course that has the potential for cyber sabotage and other forms of politics by other means.
So it sounds like just that brief history of the way things have been moving, that and probably everyone would think this just from reading their newspaper, that the scope of the security threat is just growing like crazy. Is that true from your vantage point? And why do you think that is, if so?
What we're seeing is an incredible increase every year in the amount of threats. We are at a point where we see almost 1 million new pieces of malware every single day. I think there's a driver for this, and it's really that our move to the virtual world has led criminals to the virtual world as well. With a minimum amount of technical skills, one can get involved in crime, and that crime can be done from a distance, and it can be quite profitable, and it's very difficult for law enforcement to catch these people. Now, instead of walking up to somebody, knocking them down, and stealing their purse or their wallet or their watch, you can do it from one country using computers in another country, and the ultimate victim is in a third. Whose jurisdiction is that? Who's responsible? It takes a lot of coordination between law enforcement, takes a lot of technical expertise on their part, so it can be very complicated to find these people and to prosecute them. So it's a lot safer for the bad guys to move to the virtual world.
Wow, that makes a lot of sense. Um, in the class, in this Coursera class on software security, we've spent a lot of time looking at the root causes for some of the vulnerabilities that adversaries like the ones you speak of are exploiting, these sophisticated hackers who are able to effectively repurpose software from what it was intended to do to something nefarious that they can take advantage of. And we've looked at things like the classic buffer overflows to format string attacks to web-based security threats too, like SQL injections and cross-site scripting and cross-site request forgery. I wonder if you could say a little bit about the trends in terms of vulnerabilities, the root causes of those vulnerabilities. Does the data that you have a look at, that you have access to, say anything about these vulnerabilities, which maybe are the more important?
Well, if it's okay with you, I'd like to go back and actually talk about, we're focused on what gets in the newspapers about these very sophisticated hackers who use vulnerabilities. Unfortunately, there is an underground economy with an infrastructure in place that allows even people that aren't that sophisticated to use these vulnerabilities. There are people that make toolkits. And the way they sell those toolkits is that it has a lot of functionality. You don't need to know much to be able to use this toolkit to attack someone. And these toolkits are always refreshed with the latest vulnerabilities. So you always have fresh vulnerabilities and to use things that people aren't aware of, haven't patched yet. So this really becomes a selling point for these toolkits. It's a way for them to make more money, and it enables people with very little technical skills to get into this game and to rip us off. From a trend perspective, we have seen an increase in the number of vulnerabilities found every year. That continues to trend upward. Some of this, of course, is the number of lines of code continue to increase. So it's probably natural, but it also says that we haven't done a great job of making that new code have less vulnerabilities in it. Despite all our efforts, we are not keeping up. And there is an active underground group of users who are looking for those vulnerabilities to exploit them. So we really need to step up our efforts to avoid putting those vulnerabilities in the first place. And when we do have them, get them patched, updated, and get that out to all the people using that software as soon as we can.
That makes a lot of sense. One of the elements of a reasonable security posture is when those vulnerabilities inevitably do remain, to respond to them is to use something like antivirus. You mentioned a couple of Symantec products before. I wonder if you could tell us a bit more about how antivirus works and what its role is in someone's security posture.
Absolutely. Historically, antivirus is a pattern matching type technology. We know what a virus looks like. We will write a signature or a fingerprint that can identify it when we scan a system. So we'll know it when we see it. When we see it, we'll either remove it from your machine or we'll stop it from getting on your machine overall. We've had to get a bit more sophisticated with antivirus because of the amount of malware that's written. The bad guys use something called variants. So they have tools that will create versions that look slightly different than the one they wrote. And that tool will create thousands of these new variants in order to try to evade detection. So we've put in heuristic technology, we've used machine learning, we've taken steps to increase our ability to catch things beyond exactly matching them with a pattern or fingerprint. We've also invested in other technologies, and when we talk about technology or software that you're running on your desktop to protect you, we don't even say antivirus anymore. We say endpoint protection, because we're using network-based protection, IPS protection, to look for signs of a connection to a command and control server or one of these exploits or vulnerabilities being used. If we can catch the exploit or the vulnerability or the exploitation of that vulnerability, it doesn't matter what the malware is, we can block it. So we have that type of technology. We use behavior blocking technology, things that file is doing on a machine looks like malware, so it must be malware. And we've even introduced technologies like reputation. Where have we seen this file? What machines have it been on before? What are those types of machines? How prevalent is it in the wild? Looking at different factors, so not even having seen that file, but knowing things about it, we can determine whether it's malware or not. So it takes a whole host of technologies to protect people today.
So it sounds like these technologies, in the beginning, or a few moments ago, you pointed out the importance of getting that software fixed and getting the patches out, and users actually applying those patches. And then at the same time, we have these various technologies, whether it's scanning files for signatures or looking at messaging patterns or protocols being used and so on, that all of these things are sort of working together to identify behavior, but in the end, you're not going to solve the problem of buggy software. Ultimately, the software needs to be fixed, and these other technologies are complementary in identifying potentially malicious behavior and stopping it before it's able to exploit things. Do I have that right?
Yeah, absolutely. We're trying to cover during that period while the patch is being developed and distributed out, and we're going to do the best we can until that vulnerability has been patched.
Okay, excellent. So I'm wondering if if Symantec has any advice based on, well, if you have any advice, I suppose, based on your perspective from seeing the exploitation of vulnerabilities and seeing these various trends, at how maybe we could do a better job of building security in, maybe avoiding those vulnerabilities in the first place. I mean, maybe it's fair enough to say that really you're operating outside of that space in order to protect us in that window. But I wonder if you have any insights based on your observation of all of these threats and attacks about maybe how we could build software a little bit better. What are the most important things to focus on, assuming we're going to get some things wrong? What are the things we really ought to try harder to get right to make software better?
I think the first step is really recognizing the problem, that the software that you write can be used for other purposes and put the users of that software at risk. And I don't think a lot of people think of that responsibility they have when they write that code. We often see, especially startups who are anxious to get software out in the marketplace to acquire customers. And so the most important thing is to have some functionality somebody wants to use. Security tends to be an afterthought. When the first problem happens, then we'll address it. It's really not a good business plan, and in the end, you shake the confidence of your customers in you and your brand. We think, first of all, it needs to be built in. So that's why courses like this are very exciting for us, that we're training people to think about this when they develop the software. The other thing is to recognize that there are a lot of people out there that are going to spend a lot of time thinking about this and trying to break your systems. And that so part of your process may be to have somebody do that before you release it. So for all the testing you'll do, maybe you need to do some type of pen testing, of whether it's internal to your organization or external, but have somebody come in there and try to break it for you before it's released rather than once it's out in the wild.
It's great that you mentioned that. So a little bit later on in this course, one of the last week, in fact, we do talk about penetration testing, and we interview a guy from a penetration testing company, Eric Ames, to talk about penetration testing. And it's really a fascinating area because you get to put that black hat on, but for the ultimate purpose of revealing the bugs, as you say, before they're exploited in the wild. So I know a lot of students are excited about that kind of activity.
Yeah, it's a great exercise to go through.
So that kind of relates back to this a broader question, which is um, undergraduate education. So I'm a professor in computer science at the University of Maryland, and I think we have a great curriculum. But I know that computer science is really broad and covering uh, the goal of covering so many different courses, some important things like maybe some aspects of computer security get left out, and that's certainly true in our curriculum. If you don't in some ways look for security, it's not necessarily going to find you, and I suspect it's true in other curricula. So I wonder, what's your view from being in the industry about stuff that maybe students who are interested in computer security really ought to be learning in their course curricula? If they have an opportunity, what should they take? What should maybe university curricula be doing differently to better train up people to be ready for careers such as yours or in the field?
Well, I think the fundamentals are that build you need, as you've said, you need to bake security into the process. So that really needs to be part of every application you build. And I think probably part of the core when you learn to computer program, it probably you should be being taught these best practices alongside that course. When it's done afterwards, it's always more difficult to do. So first steps are terrific that we're teaching this sort of information and that people are learning it. They absolutely have to have those skills in order to create good code. So the sooner they learn it and the more integrated it is with their effort to learn coding overall, I think the better off we'll all be.
I wonder if you could open up your crystal ball a little bit and look at what you see as potential future outcomes, the long-term prognosis for computer security. What might happen and what might we need to do in order to prevent the worst from happening looking ahead?
Well, I would say that almost any crime, any type of scam or con that you can think of has moved to the internet or is in the process of moving it to the internet. And so we will continue to see crime move there. It'll continue to evolve. It may look slightly different, but it will be because it's using the internet, but it'll be bigger and faster. So we have an obligation to try to protect ourselves from that. The other trend clearly is that countries are looking at this where are all adding their own kind of cyber forces, not only for defense, but also for offense as well. And so this is an ongoing trend that we will continue to see. I don't expect to see the amount of malware that's created or crime done with it go down. That will continue to grow. But I think what's happened is our systems are becoming even more complex and more difficult for one person to understand. But one determined person looking for a hole in the world or a way to break in then does have an advantage. Probably the biggest factor changing things, of course, will be the Internet of Things as we get billions of devices that are connected to the Internet, that are running operating systems, but may not have a user interface, may not be something that we ever directly interface with. But we'll have software, we'll have vulnerabilities, and people will look to take advantage of those. And so I think that may be, or definitely will be even a bigger challenge than we have on PCs and phones. It's these devices that sit in our offices, sit in our homes, that we never connect to, but connect us. And that may very well be, and in fact, we've seen already being taken advantage of.
Yeah, frankly, that's a frightening prospect that even more stuff around you is connected and potentially vulnerable. And if the people that are putting this stuff together are not thinking about security and the products to sort of defend them in the meantime are need to figure out this new landscape, we're just going to be that much more vulnerable in the short term.
Yeah, I'll give you a great example. There's a very famous story of a baby monitor being hacked. Dad walks into his room, or his daughter's room, and somebody's shouting obscenities through the speaker of that webcam that he uses to watch his daughter and check up on her over his phone. Well, there's a vulnerability in that webcam that allowed an attacker to get in there, control the camera and the speaker. Now, if you had gone to the website of that manufacturer, they knew that that vulnerability was there, and they would tell you that all you need to do is flash the ROM in order to fix that vulnerability. Well, how many parents of newborns buying a nanny cam or a webcam would think to go to the website in the first place, think that there could be a vulnerability in it, and how many of them know how to flash a ROM? Right? But the manufacturer hadn't thought about that either and really didn't have a good way to help these people out. That's clearly a challenge for us moving forward.
Wow, that's really interesting. So maybe as a final thought, I have been to Symantec's website. You mentioned Symantec Research. There's a lot of great information there that's available for people to find about trends and threats. I wonder if you could say a little bit about the resources that you have available for people to learn more about the current state of security, or to learn about techniques and ideas that you guys are pursuing that maybe they could also learn more about.
Yeah, absolutely. On our site, and specifically on the security response part of the site, we are writing blogs and putting together white papers on the latest attacks, the information we've been able to glean on attack groups and the methods that they use. So there's a lot of fascinating information there. And once a year, we gather all the information that we've collected through the year, and we put it together, compile it to kind of get a sense of where the threat landscape is and where it's going. It's called the Internet Security Threat Report. The new one will actually be out April 14th, and so we'll look back on 2014, what happened, and what that means for the future.
Okay, great. Well, thank you so much for taking this time to speak with me and for our learners in this Coursera course on software security. It's been really interesting. So thank you for your time.
My pleasure, and good luck to everybody on the course. It's something we really need people to understand.